Good morning, students. I am Ms. Republica Borgohain, Assistant Professor, Assam Downtown University, Guwahati, Department of Pharmaceutical Science. So today I will be going to discuss regarding the properties of enzymes. So the enzymes possess many outstanding characteristics. These are, first one is the colloidal nature. So enzyme molecules are of giant size. Their molecular weights range from 12,000 to over 1 million. They are therefore very large compared with the substrates or functional groups they act upon. It has been observed that the molecular weights of many enzymes prove to be approximately an n-fold multiple, where n is an integer of 17,500, which is found to be an unit in most proteins. On account of their large size, the enzyme molecules possess extremely low rates of diffusion and form colloidal systems in water. Being colloidal in nature, the enzymes are non-dialysable, although some contain dialysable or dissociable component in the form of coenzyme. So the second nature is catalytic nature or effectiveness. An universal feature of all enzymatic reactions is the virtual absence of any side products. They are recovered as such without undergoing any qualitative or quantitative change. This is the reason why they, in very small amounts, are capable of catalyzing the transformation of a large quantity of substrate. The catalytic potency of enzymes is exceedingly great. The catalytic power of an enzyme is measured by the turnover number or molecular activity. The number of substrate molecules converted into product per unit time when the enzyme is fully saturated with substrate. The value of turnover number varies with different enzymes and depends upon the conditions in which the reaction is taking place. However, for most enzymes, the turnover numbers fall between 1 to 10 to the power 4 per second. The third one is the specificity of enzyme action. With few exceptions, the enzymes are specific in their action. Their specificity lies in the fact that they may act on one specific type of substrate molecule, on a group of structurally related compounds, on only one of the two optical isomers of a compound, or on only one of the two geometrical isomers. Accordingly, four patterns of enzyme specificity have been recognized. They are absolute specificity. So in case of absolute specificity, some enzymes are capable of acting on only one substrate. For example, urease, it acts only on urea to produce ammonia and carbon dioxide. Similarly, carbonic anhydrase brings about the union of carbon dioxide with water to form carbonic acid. That means water plus carbon dioxide, when it reacts with carbonic anhydrase, then it gives carbonic acid, that is H2CO3. Second one is group specificity. Some other enzymes are capable of catalyzing the reaction of a structurally related group of compounds. For example, lactic dehydrogenase, that is LDH, catalyzes the interconversion of pyruvic and lactic acids and also of a number of other structurally related compounds. Pyruvic acid, that is CH3COCOOH plus NADH plus H plus, when it reacts with lactic dehydrogenase, then it forms lactic acid plus NAD plus. Third one, optical specificity. The most striking aspect of specificity of enzymes is that a particular enzyme will react with only one of the two optical isomers. For example, arginase acts only on L-arginine and not on its D isomer. Similarly, D-amino acid oxidase, it oxidizes the D-amino acids only to the corresponding keto acids. Although the enzymes exhibit optical specificity, some enzymes, however, interconvert the two optical isomers of a compound. For example, alanine racemase catalyzes the interconversion between L and D-alanine. So L-alanine, when it reacts with alanine racemase, it gives D-alanine. Fourth one, the geometrical specificity. Some enzymes exhibit specificity towards the cis and trans forms. As an example, fumarase catalyzes the interconversion of fumaric and malic acids. It doesn't react with malic acid, which is the cis isomer of fumaric acid, or with D-malic acid. The degree of specificity of the enzymes for substrate is usually high and sometimes virtually absolute. Proteolytic enzymes catalyze the hydrolysis of a peptide bond. Many proteolytic enzymes, that is pepsin, trypsin, chymotrypsin, catalyze a different but related reaction, namely the hydrolysis of an ester bond. These enzymes vary markedly in their degree of specificity. For example, subtilisin, a bacterial enzyme, does not discriminate the nature of the side chains adjacent to the peptide bond to be cleaved. Another enzyme, pepsin, prefers bonds involving the carboxyl and amino groups of D-carboxylic and aromatic amino acids respectively. Since the bonds attached are usually located in the interior of the protein substrate, pepsin is called an endopeptidase. Trypsin likewise is an endopeptidase but is quite specific in that it splits peptide bonds in which carboxylic group is contributed by either lysine or arginine only. Chymotrypsin preferentially splits peptide bonds in which the carboxyl group is from an aromatic amino acid. Now, alteration of enzyme specificity. The specificity of enzymes is altered by physiological behavior. So, we can discuss that lactose synthesis, it catalyzes the synthesis of lactose, a sugar consisting of a galactose and a glucose residue, in the mammary glands. It consists of a catalytic subunit and modifier subunit. The catalytic subunit alone cannot synthesize lactose. Instead, it has a different role of catalyzing the attachment of galactose to proteins that contain a covalently linked carbohydrate chain. The modifier subunit alters the specificity of the catalytic subunit so that it links galactose to glucose to form lactose. The level of modifier subunit is under hormonal control. During pregnancy, the catalytic subunit is formed in the mammary glands and very little modifier subunit is formed. But at the time of childbirth, that is parturition, the hormonal levels change significantly and the modifier subunit is synthesized in great quantities, thus resulting in the production of large amounts of lactose. So this is the reaction which occurs in the alteration of enzyme specificity in case of lactose synthetase. Now comes the active site. As the substrate molecules are comparatively much smaller than the enzyme molecules, there should be some specific regions or sites on the enzyme for binding with the substrate. Such sites of attachment are variously called as active sites or catalytic sites or substrate sites. So, properties of active site. The active site occupies a relatively small portion of the enzyme molecule. The active site is neither a point nor a line or even a plane, but is a three-dimensional entity. It is made up of groups that come from different parts of the linear amino acid sequence. For example, lysosome has 6 subsites in the active site. The amino acid residues located at the active site are 35, 52, 59, 62, 63, and 107. Usually, the arrangement of atoms in the active site is well defined, resulting in a marked specificity of the enzymes. Although cases are known where the active site changes its configuration in order to find a substance, which is only slightly different in structure from its own substrate. The active sites binds the substrate molecule by relatively weak forces. The active sites in the enzyme molecules grooves or crevices from which water is largely excluded. It contains amino acids such as aspartic acid, glutamic acid, lysine, serine, etc. The side chains groups like COOH, NH2, CH2OH, etc. serve as catalytic groups in the active site. So in my next video, I will be discussing about the Fischer's lock and key model, how it works with the help of the active site. Thank you.